December 15th, 1941. Bataan Peninsula, Philippines. In the abandoned wreckage of American retreat, Japanese Captain Hideo Miyata discovered something that would shatter everything his engineers believed about Western automotive design. A single Willys MB Jeep, bullet scarred but still running after weeks in the jungle. Miyata pulled one lever, 4 wheels engaged instantly. The engine idled at 600 RPM with mechanical precision he had never heard from any Japanese vehicle. 60 horsepower from just 134 cubic inches. The same power output Ford extracted from their massive V8 engines. This was supposed to be impossible. Japanese automotive doctrine taught that American cars were over-engineered, wasteful, built for comfort rather than durability. Yet here sat proof of something different. Something that suggested Japan's entire understanding of industrial capability might be wrong. The Imperial Army immediately shipped the captured Jeep to Toyota with a simple order. Build us 500 copies within 6 months. What happened next would expose the terrifying gap between Japanese confidence and American industrial reality. The morning sun filtered through the dense canopy of the Bataan Peninsula as Captain Hideo Miyata picked his way through the debris field of American retreat. Abandoned equipment lay scattered across the jungle floor, helmets, ammunition boxes, field radios smashed beyond repair. But there, partially concealed beneath a camouflage net near what had once been a motor pool, sat something extraordinary. The Willys MB Jeep appeared almost pristine except for 3 bullet holes spider webbing across the windshield. Miyata approached cautiously, his engineering instincts immediately cataloging details. The vehicle's proportions seemed wrong by Japanese standards, too compact, too purposeful. None of the elaborate ornamentation that marked Japanese military vehicles, just clean lines and functional design. He climbed into the driver's seat, noting the simplicity of the dashboard, a few gauges, basic switches, nothing excessive. The key remained in the ignition. Miyata turned it, and the Go Devil engine coughed to life with a sound that made him freeze. 600 revolutions per minute, steady as a metronome. In his 8 years designing engines for Toyota before the war, he had never heard such mechanical precision from a 4-cylinder motor. Miyata engaged the clutch and shifted into first gear, feeling the transmission's smooth operation. Then he reached for the small lever mounted beside the gear shifter. The transfer case control he had read about in intelligence reports but never seen. One simple pull, and he felt the front wheels lock into the drivetrain. 4-wheel drive, engaged as easily as turning on a light switch. He drove the Jeep in a wide circle around the abandoned motor pool, testing its capabilities. The vehicle climbed a steep embankment that would have stopped any Japanese reconnaissance car. It powered through muddy ground that would have mired their Type 95 Kurogane. Most remarkably, it did all of this while maintaining that steady mechanical rhythm from the engine bay. Miyata shut off the engine and popped the hood, revealing the Go Devil's compact architecture. 134 cubic inches of displacement according to the casting marks. His mental calculations were swift and disturbing. This small American engine produced 60 horsepower, the same output Ford achieved with their massive V8. Japanese engines of similar size barely managed 35 horsepower, and only for brief periods before overheating or mechanical failure. He examined the engine block more closely, running his fingers along the machine surfaces. The tolerances appeared impossibly tight. The valve train operated with precision that suggested manufacturing capabilities beyond Japanese standards. Every component fit together with an exactness that spoke of systematic engineering rather than the hand-fitting methods still common in Japanese factories. The technical implications struck him with growing force. This was not just a superior vehicle. It was evidence of an entire industrial ecosystem that Japan had fundamentally misunderstood. American automotive engineering had evolved far beyond the crude quantity over quality stereotype that Japanese military doctrine assumed. Miyata climbed back into the driver's seat and started the engine again, letting it idle while he processed what he was seeing. In pre-war Tokyo, he had dismissed American automobiles as wasteful luxury items, built for smooth roads and comfortable driving rather than military durability. The evidence before him suggested a completely different reality. He shifted into reverse and backed the Jeep toward a fallen tree, engaging the four-wheel drive system again. The vehicle climbed over the obstacle with mechanical confidence that belied its compact size. No wheel spin, no hesitation, just steady traction that distributed power exactly where needed. The radio crackled to life in his backpack. Colonel Tanaka's voice cut through the static, demanding a status report on captured equipment. Miyata keyed the microphone, choosing his words carefully. "Sir, I have located an intact American reconnaissance vehicle. It appears to demonstrate capabilities that warrant immediate technical evaluation." "Capabilities, Captain?" "The four-wheel drive system operates flawlessly, sir. The engine produces power levels that exceed our current estimates of American automotive technology. I recommend immediate shipment to our engineering facilities for detailed analysis." There was a pause. "Are you suggesting this single vehicle represents some significant advancement, Miyata?" Miyata looked at the Jeep's clean dashboard, listened to the steady idle of its Go Devil engine, felt the solid construction beneath his hands. "Sir, I believe this vehicle represents a level of systematic engineering that our intelligence assessments may have underestimated." 2 hours later, a recovery team arrived with a transport truck. As they loaded the captured Jeep, Miyata made detailed notes in his field journal. Weight distribution, suspension geometry, the elegant simplicity of the transfer case design. Each observation reinforced his growing conviction that Japan faced an industrial challenge more formidable than anyone in Tokyo understood. The Jeep disappeared onto the transport truck bound for the Toyota engineering facility in Kuromo. Miyata sealed his initial report in a dispatch pouch, knowing it would reach Imperial Army headquarters within days. His recommendation was direct and unambiguous. Assign Japan's best automotive engineers to reverse engineer this vehicle immediately. But as the transport truck disappeared into the jungle, Miyata felt the first stirring of doubt about Japan's ability to replicate what he had discovered. The American Jeep represented more than clever engineering. It embodied an approach to manufacturing that might be fundamentally different from anything Japan had attempted. The question that would define the next 3 years of warfare had crystallized in his mind during those 2 hours with the captured vehicle. Could Japanese ingenuity overcome American industrial systematization? The answer would determine far more than automotive production schedules. It would reveal the true balance of industrial power between two nations locked in total war. The captured Willys MB arrived at Toyota's Kuromo plant on a gray February morning in 1942, shrouded in canvas and accompanied by strict orders from Imperial Army headquarters. Chief Engineer Takatoshi Arisawa watched the transport truck disappear through the factory gates, leaving behind what appeared to be Japan's greatest reverse engineering challenge since the Meiji Restoration. Arisawa assembled his most experienced team in Building 7, the facility's most secure engineering bay. 12 senior engineers, 3 metallurgists, and 2 draftsmen gathered around the American vehicle as Arisawa pulled away the canvas covering. The Jeep sat under the harsh fluorescent lights like a mechanical specimen awaiting dissection. "Gentlemen," Arisawa announced, "we have 6 months to build 500 copies of this vehicle. The Imperial Army expects delivery by August." He paused, studying their faces. "We begin with complete disassembly and documentation of every component." The process began with methodical precision that had characterized Toyota's engineering approach since the company's founding. Senior engineer Kichiro Yamamoto photographed each stage of disassembly, while draftsman Hiroshi Nakamura created detailed sketches from multiple angles. Every bolt, every gasket, every component received measurement to hundredths of millimeters. The engine bay revealed the Go Devil's sophisticated architecture in stunning detail. Arisawa himself removed the cylinder head, exposing machining tolerances that made him pause mid-motion. The combustion chambers showed uniform finish quality across all 4 cylinders. The valve seats were cut with precision that suggested manufacturing equipment Toyota did not possess. The compression ratio appears to be 7.6 to 1, reported metallurgist Saburo Ito after careful measurement. Our Type C engine operates at 6.5 to 1 maximum before detonation problems develop. Arisawa made notes in his engineering journal, documenting every specification. The Americans had achieved higher compression through superior fuel quality and metallurgy, extracting more power from each combustion cycle. Japanese aviation fuel could sustain these compression ratios, but automotive gasoline would cause destructive engine knock. The transmission disassembly revealed equally impressive engineering. 3 forward speeds plus reverse, synchronized shifting, and robust internal components that showed minimal wear despite obvious field use. The transfer case demonstrated mechanical elegance that impressed even veteran Toyota engineers. A simple lever engaged front-wheel drive through a robust gear reduction system. Within 2 weeks, Arisawa's team had created complete blueprints of every major component. The differential housing, suspension geometry, steering system, and electrical components all received exhaustive documentation. On paper, the American design appeared entirely achievable using existing Japanese manufacturing capabilities. But the first prototype told a different story. Designated AK-10 by Toyota's internal coding system, the Japanese copy incorporated their existing 2.3-liter Type C engine instead of replicating the Go Devil. Japanese steel quality simply could not sustain the American engine's compression ratios and operating stresses. The AK-10's engine produced 45 horsepower compared to the original 60, but Arisawa initially viewed this as acceptable compromise. More troubling was the transfer case, copied precisely from American blueprints, but manufactured using Japanese steel alloys and heat treatment processes. The prototype's first test run at Toyota's proving ground lasted exactly 12 hours before catastrophic failure. The transfer case gears stripped under load, leaving the AK-10 immobilized on a test hill that the original Jeep had climbed repeatedly without difficulty. Arisawa examined the failed components under magnification, noting the crystalline fracture patterns in the gear teeth. Japanese metallurgy could produce the correct shapes and dimensions, but not the material properties that made those shapes functional under stress. The Americans were achieving hardness values and fatigue resistance that Japanese steel science could not match. "We can copy the form," Arisawa wrote in his evening journal entry, "but not the essence. Their metallurgy appears to be generations ahead of ours." The admission troubled him deeply, contradicting everything he had assumed about relative industrial capabilities between Japan and America. A second prototype incorporated modified gear ratios and reinforced components lasting 38 hours before different mechanical failures disabled the vehicle. A third prototype survived 62 hours but developed severe engine knock that limited power output to 32 horsepower, barely adequate for reconnaissance, useless for cargo hauling. By late spring, Arisawa's team had produced their most successful prototype yet. The fourth AK-10 looked nearly identical to the original Jeep and demonstrated reasonable off-road capability during controlled testing. Engine power reached 47 horsepower through careful tuning, and the reinforced transfer case survived over 100 hours of operation. Toyota's management declared the reverse engineering project successful. Production planning began for the Imperial Army's order of 500 vehicles. Arisawa submitted his technical report with guarded optimism, noting remaining challenges but expressing confidence that Japanese engineering had mastered the American design principles. Yet, privately, he harbored growing concerns about mass production capabilities. Each prototype had required extensive hand fitting and individual component adjustment. The machining tolerances that made American components interchangeable demanded precision equipment Toyota possessed in limited quantities. Quality control systems that ensured consistent performance across hundreds of vehicles remained largely theoretical. The original Willys MB sat in the corner of Building 7 throughout the reverse engineering process, a constant reminder of American industrial achievement. After 18 months of testing and evaluation, it remained mechanically sound and operationally reliable. Arisawa would start its engine periodically. Listening to the steady 600 RPM idle that had impressed Captain Miyata on Bataan Peninsula. The contrast with Toyota's prototypes was becoming undeniable. Japanese engineering could approximate American designs, but the systematic approach to manufacturing quality that made those designs practical for mass production remained elusive. As summer approached and the Imperial Army's deadline loomed, Arisawa began to suspect that Japan had underestimated not just American engineering capability, but the entire industrial ecosystem that supported it. The Go Devil engine's technical specifications haunted Arisawa's dreams throughout the spring of 1942. 60 horsepower and 109 pound-feet of torque from just 134 cubic inches represented engineering achievement that challenged fundamental assumptions about internal combustion design. More disturbing was the engine's operational endurance. Willys guaranteed 100 hours of continuous operation at 4,400 RPM, a performance standard that exceeded Japanese capabilities by factors Arisawa struggled to comprehend. He had disassembled Delmar Roos's masterpiece component by component, documenting every innovation with obsessive precision. The fully pressurized lubrication system pumped oil to every bearing surface under consistent pressure, eliminating the splash lubrication methods still common in Japanese engines. The counterbalanced crankshaft reduced vibration to levels that allowed sustained high RPM operation without mechanical fatigue. Insert bearings replaced the plain bronze bushings that Japanese manufacturers considered adequate, providing durability under loads that would destroy conventional designs. But it was the aluminum pistons that revealed the true gap between American and Japanese metallurgy. Arisawa had never seen aluminum castings with such dimensional stability and heat resistance. Japanese aluminum alloys warped under the thermal stresses that these American pistons absorbed routinely. The piston rings maintained compression across temperature ranges that would cause Japanese components to seize or leak catastrophically. Their material science is decades beyond ours, Arisawa confided to his deputy Yamamoto during one of their evening engineering sessions. We can machine components to their specifications, but we cannot replicate the metallurgical properties that make those specifications functional. The numbers told an increasingly stark story. Toyota's most advanced prototype, incorporating every lesson learned from 18 months of development, produced 45 horsepower from their 2.3-liter Type C engine. Reliability testing revealed engine failure after 22 hours at maximum RPM, less than one-quarter the endurance Willys achieved routinely. Japan's existing military vehicles performed even worse by comparison. The Type 95 Kurogane, considered adequate for reconnaissance duties, generated 33 horsepower from its V-twin engine. Adequate for carrying 2 soldiers across reasonable terrain, but useless for the cargo hauling and tactical mobility that made American Jeeps revolutionary. The weight-to-power ratio differences were devastating. American Jeeps could climb grades and traverse obstacles that stopped Japanese vehicles completely. Arisawa spent countless hours studying the Go Devil's combustion chamber design, noting how Roos had optimized flame front propagation and heat dissipation. The cylinder head incorporated cooling passages positioned with mathematical precision, maintaining optimal operating temperatures under conditions that would cause Japanese engines to overheat. The valve timing and lift profiles extracted maximum power from each combustion cycle while minimizing mechanical stress on reciprocating components. The carburation system demonstrated similar sophistication. The Carter YF carburetor maintained fuel-air ratios across throttle positions and environmental conditions that challenged Japanese fuel delivery technology. Altitude compensation, cold weather starting, and consistent mixture control under varying loads. Each requirement pushed Japanese manufacturing capabilities beyond proven limits. By late summer, Toyota's engineering team had achieved their most successful reverse engineering attempt yet. The 5th generation AK-10 prototype demonstrated remarkable similarity to the original Jeep's external appearance and basic functionality. Road testing at the Fuji Proving Grounds showed acceptable performance for reconnaissance missions, reasonable off-road capability, and mechanical reliability approaching Japanese military standards. Arisawa submitted his preliminary report to Imperial Army headquarters with cautious optimism. The AK-10 could fulfill basic transportation requirements, providing 4-wheel drive capability that surpassed anything currently in Japanese military inventory. Engine power, while below American standards, remained adequate for most anticipated missions. Manufacturing could proceed using existing Toyota production facilities with minimal retooling. Yet the technical challenges that remained unsolved troubled him deeply. The AK-10 required 340 man-hours to manufacture compared to the 130 man-hours American factories needed for identical capability. Each vehicle demanded individual adjustment and hand fitting that made mass production problematic. Quality control systems that ensured consistent performance across hundreds of units remained theoretical rather than practical. More fundamentally, the AK-10's 45 horsepower engine could not sustain prolonged, high-power operation without mechanical degradation that shortened operational life significantly. Field testing revealed transmission problems, transfer case failures, and electrical system weaknesses that reflected the gap between copying American designs and mastering American manufacturing processes. The original Willys MB, now veteran of countless test cycles and engineering evaluations, continued operating with mechanical precision that mocked Japanese efforts to replicate its capabilities. Arisawa would start the Go Devil engine each morning, listening to its steady idle while contemplating the industrial achievement it represented. American automotive engineering had evolved through decades of civilian production experience that Japan simply lacked. Detroit's assembly lines had refined manufacturing processes through millions of vehicles, developing quality control systems and parts standardization that enabled mass production of complex mechanical systems. Japanese automotive industry, producing fewer than 13,000 vehicles annually, possessed neither the experience nor the infrastructure to match American capabilities. The realization struck Arisawa with growing force as autumn approached. Japan could build individual prototypes that approximated American performance, but they could not systematically manufacture hundreds of vehicles with consistent quality and reliability. The Go Devil engine represented not just superior design, but an entire industrial ecosystem that Japan had failed to understand or develop. In his private engineering journal, Arisawa recorded the admission that would define his post-war career. "We have succeeded in copying their form, but we have failed to comprehend their essence." American superiority lies not in individual components, but in the systematic approach to manufacturing excellence that makes those components practical for mass production. The Imperial Army's order arrived at Toyota headquarters on October 3, 1942, with the bureaucratic precision that characterized Japanese military administration. 200 AK-10 vehicles for immediate deployment to the Burma theater. Delivery required within 60 days to support General Ida's offensive operations against British positions along the Chindwin River. Arisawa stared at the production schedule his manufacturing supervisors had prepared, feeling the weight of industrial reality crushing his engineering optimism. Toyota's Koromo plant could theoretically produce 34 vehicles per day using existing assembly line capacity. But the AK-10 was not a conventional Toyota product. It was a complex, reverse-engineered system that defied every manufacturing assumption upon which Japanese automotive production operated. The first crisis emerged within days of production startup. AK-10 transmissions required precision gear cutting that Toyota's machinery could not consistently achieve. Each transmission demanded individual adjustment by skilled machinists, creating bottlenecks that reduced daily output to fewer than 12 vehicles. Quality control inspectors rejected nearly 30% of completed transmissions due to tolerance problems that would cause premature failure in field conditions. "We are building prototypes, not production vehicles," Arisawa confided to his manufacturing director during a tense planning session. "Every AK-10 requires custom fitting and individual engineering attention. This is not mass production, this is expensive handicraft." The transfer case problems proved even more intractable. Japanese steel alloys could not sustain the operating stresses that American metallurgy handled routinely, forcing Toyota engineers to redesign gear ratios and reduce power transmission capabilities. The resulting transfer cases lasted longer during testing, but delivered significantly less torque to the front wheels, compromising four-wheel drive performance under load. By late October, Toyota had completed 47 AK-10 vehicles, each representing nearly 2 weeks of intensive labor by their most skilled technicians. The Imperial Army's deadline loomed with mathematical certainty. 153 vehicles remaining, 37 days available, current production rate suggesting completion sometime in early January. Arisawa authorized double shifts in weekend production, pulling engineers from civilian automotive projects to support AK-10 assembly. The factory operated around the clock with welding sparks illuminating Building 7 throughout the night shifts. But increased production tempo only magnified existing quality problems, forcing higher rejection rates and longer rework cycles. The vehicles that did pass final inspection revealed disturbing performance variations. AK-10 number 23 produced 48 horsepower and demonstrated excellent off-road traction. AK-10 number 31 generated only 41 horsepower and suffered transmission problems during road testing. Individual manufacturing variations, negligible in conventional Toyota products, became critical deficiencies in vehicles intended for military service. American automotive plants, Arisawa realized with growing clarity, had solved these production challenges through systematic standardization that Japanese industry had never developed. Ford's GPW and Willys' MB components were completely interchangeable, despite being manufactured by different companies using different equipment. Japanese manufacturers produced custom parts for each model, making quality control and part supply a nightmare of individual specifications. The first field reports from Burma arrived in November, delivered by courier from Imperial Army headquarters with classification levels that restricted access to senior engineering staff. Arisawa read the operational summary with mounting dread. Of 47 AK-10 vehicles deployed to Burma Theater, 31 are currently inoperative due to mechanical failure. Remaining 16 vehicles show severe engine wear after approximately 200 hours of field operation. The detailed failure analysis painted a devastating picture of Japanese manufacturing inadequacy. Transmission failures occurred within days of deployment, stranding AK-10 vehicles in locations where recovery was impossible. Engine seizures developed after minimal operation under tropical conditions that American Jeeps handled without difficulty. Transfer case breakdowns eliminated four-wheel drive capability, reducing tactical mobility to levels below existing Japanese reconnaissance vehicles. Most critically, spare parts availability approached zero. When AK-10 transmissions failed in Burma, there were no replacement units available. When engines seized due to inadequate lubrication systems, there were no spare blocks in military supply chains. Each disabled AK-10 became an irreplaceable loss rather than a repairable asset. The field commander's recommendation struck Arisawa like physical blow. Request immediate return to Type 95 Kurogane vehicles despite performance limitations. AK-10 reliability insufficient for operational requirements. Recommend termination of production pending fundamental design improvements. Arisawa walked through Building 7 that evening, observing the continued assembly of vehicles he now knew were destined for failure. Night shift workers installed engines that would seize within weeks, transmissions that would strip their gears under operational loads, transfer cases that would fracture when soldiers demanded four-wheel drive performance. The original Willys MB sat in its corner position, mechanically sound after 20 months of continuous testing and evaluation. Arisawa started its Go Devil engine, listening to the steady rhythm that had operated flawlessly since its capture on Bataan Peninsula. 600 RPM, precise as Swiss clockwork, durable as geological time. In his engineering journal that night, Arisawa recorded the brutal mathematics of Japanese industrial defeat. American Jeep production exceeds 600,000 units across multiple manufacturers with complete parts interchangeability. Japanese AK-10 production totals 87 units with individual variations so severe that components cannot be exchanged between vehicles. We have attempted to copy their design but failed to comprehend their manufacturing philosophy. The admission extended beyond automotive engineering into fundamental questions about Japanese industrial capacity. America possessed systematic approaches to quality control, part standardization, and mass production that enabled complex mechanical systems to be manufactured reliably in enormous quantities. Japan had developed individual craftsmanship and custom engineering capabilities, but lacked the industrial infrastructure for systematic mass production. By December 15th, exactly 1 year after Captain Miyata's discovery on Bataan Peninsula, Toyota quietly suspended AK-10 production after completing fewer than 100 units. The project that had begun with such confidence in Japanese reverse engineering capabilities ended in comprehensive industrial failure, leaving behind only expensive lessons about American manufacturing superiority and Japanese technological limitations. The January wind cut through the windows of Building 7 as Arisawa sat at his drafting table, composing the final report that would end Japan's most ambitious reverse engineering project. 2 years of intensive effort, hundreds of thousands of yen in development costs, and the concentrated expertise of Toyota's best engineers had produced a total of 87 functional AK-10 vehicles, fewer than Willys Overland manufactured in a single day. The numbers that filled his report told a story of industrial defeat more comprehensive than any battlefield loss. American Jeep production had reached 640,000 units by January 1943, with Ford and Willys plants delivering over 150 vehicles daily using assembly line techniques that made complex four-wheel drive systems as routine as manufacturing bicycles. Japanese total automotive production for the entire war period would barely exceed 35,000 units across all manufacturers and vehicle types. The American Jeep represents not merely superior individual design, Arisawa wrote in his official conclusion, but an entire industrial ecosystem we cannot replicate with current capabilities. Their advantage lies not in secret technologies or unavailable materials, but in systematic approaches to mass production, quality control, and part standardization that require decades of manufacturing experience to develop. The admission carried implications that extended far beyond automotive engineering. If Japan could not successfully copy a relatively simple four-wheel drive vehicle, what did this reveal about their ability to match American production in aircraft, naval systems, or industrial machinery? The Go Devil engine had become a window into American industrial capacity that illuminated capabilities Japanese intelligence had fundamentally underestimated. Arisawa's deputy, Yamamoto, reviewed the draft report with growing concern. Sir, this assessment suggests that American manufacturing superiority may be insurmountable given our current industrial base. Are we certain these conclusions are accurate? The evidence is incontrovertible, Arisawa replied, gesturing toward the production statistics that covered his desk. We can build individual prototypes that approximate their performance, but we cannot systematically manufacture hundreds of vehicles with consistent quality. Our failure rate exceeds 70% in field conditions. Their vehicles operate reliably after hundreds of thousands of units produced. The contrast with pre-war assumptions was devastating. Japanese military doctrine had dismissed American industrial capacity as quantity without quality, mass production of inferior goods designed for civilian comfort rather than military durability. The Jeep proved exactly the opposite. American factories were producing superior military equipment in quantities that dwarfed Japanese capabilities while maintaining quality standards that Japanese manufacturers could not achieve even in small batch production. The original Willys MB remained in Building 7 as silent testimony to American engineering excellence. After 24 months of continuous testing, evaluation, and operational use, it continued running with mechanical precision that mocked Japanese efforts to replicate its capabilities. The Go Devil engine had accumulated over 800 hours of operation, equivalent to 4 complete AK-10 lifespans without requiring major maintenance or component replacement. Arisawa submitted his final report to Imperial Army Headquarters in February 1943, recommending immediate cessation of reverse engineering efforts and acknowledgement that American industrial capacity exceeded Japanese estimates by factors previously considered impossible. The 20-page technical assessment documented every aspect of Japanese failure, from metallurgical limitations to manufacturing process inadequacies. The response from Tokyo arrived within days, marked with classification levels that restricted distribution to senior staff officers. Colonel Tanaka's covering letter was brief and pointed. Engineer Arisawa's assessment raises fundamental questions about our industrial planning assumptions. Forward copies to Ministry of Munitions and Naval Technical Department for immediate evaluation. But the war's momentum had already moved beyond such strategic recalculations. Japanese forces were committed to campaigns across the Pacific that assumed industrial parity with American production capabilities. The Battle of Guadalcanal had demonstrated American ability to sustain complex logistics operations across vast distances, The Doolittle raid had proven American capacity for technological surprise and long-range operational planning. The failed Jeep project now provided additional evidence of industrial disparities that Japanese leadership was reluctant to acknowledge. Arisawa found himself transferred to civilian automotive projects in March 1943, officially to support essential transportation needs, but practically to remove him from military engineering, where his conclusions about American capabilities were becoming uncomfortable truths. He spent the remainder of the war developing fuel-efficient engines and lightweight vehicles using Japanese materials and manufacturing methods, accepting limitations rather than attempting to match American standards. The captured Willys MB disappeared from Building 7 sometime in late 1943, presumably scrapped for strategic materials as Japan's resource situation deteriorated, but its lessons remained embedded in Arisawa's understanding of industrial engineering and systematic manufacturing approaches that would define his post-war career. In 1950, 5 years after Japan's surrender, an unexpected opportunity emerged from the Korean War's logistics requirements. The United States military, desperately needing additional vehicle production capacity, contracted Toyota to manufacture 100 military vehicles using Willys specifications and American quality control standards. This time, Toyota succeeded, not by copying American methods, but by developing Japanese approaches to manufacturing excellence that honored the lessons learned from the failed AK-10 project. They built vehicles that met American specifications while incorporating Japanese innovations in efficiency and quality control that would eventually revolutionize global automotive production. Arisawa, now Toyota's chief engineer, supervised the Korean War contract with deep satisfaction. The vehicles they delivered to American forces demonstrated that Japanese engineering had finally understood the fundamental lesson the captured Jeep had taught. True industrial excellence required building upon systematic manufacturing capabilities rather than simply copying successful designs. The Go Devil engine's legacy extended far beyond its wartime role. It had forced Japanese engineers to confront the reality of American industrial superiority, abandon assumptions about Western manufacturing limitations, and develop new approaches to quality and efficiency that would make Toyota a global automotive leader in the decades following the war. The captured American Jeep had taught Japanese engineers that genius was not just in the design, it was in the entire industrial civilization that created, refined, and mass-produced that design with systematic excellence, that transformed complexity into reliability.